Okay, today I'm going to talk about probability distributions. In last lecture, we introduced the probability with some basic definitions, such like randomization experiment, sample spaces, elementary outcomes, and event. And we introduced the definition for probability based on those definitions. Then we learned some basic operations about probability. In the end of the lecture, we introduced the Bayesian theorem. Today, I'm going to talk about how to link the probability distribution with the real data analysis using the random variable. So I'm first going to introduce what is random variable, and there are two types of it. One is the discrete random variable. The other is continuous random variable. Then I'm going to introduce two important probability distributions. One is for the discrete random variable. We're going to introduce the binomial distribution. The other is for the continuous random variable. It is the normal distribution. So first, a look at the definition of random variable. A random variable is a function that assigns numerical values to different events in a sample space. Usually, we denote a random variable using a capital letter, X or Y or Z, they're all capital. Then we just using the lowercase letter to denote the observed value. So for random variable, we use the capital letters. And for the random variable, there are two properties. One, it must be random, such like I assume in this class, all of the students are from the Department of Biology. Then I draw a sample from you. Then if I ask what's the department for this student, it's definitely gonna be biology. So this is no randomness. This variable is not a random variable. A random variable must be random, and also its value should be numerical values. For example, if I draw a sample from you guys, I ask the height for this student. This height could be vary from sample to sample. It's random, and it's gonna be represented by a numerical value. So this is a random variable. And another example, for this student, I ask the number of siblings for this student. It's again another random variable because it's random. Different student has the different answer, and the value is numerical. Is that okay? Two properties for the random variable. It must be random. The other must be numerical values. Even maybe for some measurement, it could be characteristic, such like gender, could be male, female. But in mathematics, we're gonna convert it into numerical value using 0 or 1 to represent the value for such kind of measurement. Is that okay? So this is the random variable. There are two types of it. One is discrete random variable. Those outcomes are a set of discrete or isolated values, such like number of siblings or gender. So those numbers are 1, 2, 3, 4 are just the discrete numbers. And the other type is continuous random variable. For the continuous random variable, its possible values cannot be enumerated. There are infinite number of possibilities for this kind of random variable. And also, it has probability 0. So I'm going to talk about this property for continuous variable later in details. I just tell you there are two types. We're going to first deal with discrete random variable. For the continuous random variable, such like student height, this value is continuous. There are infinite possibilities for the height. So that is a continuous random variable. So after we define the random variable, we're gonna assign the probability for the outcome of the random variable. For this example, we are tossing two coins. I define X, this random variable, be the number of heads. Tossing two coins, we count how many heads we get for each trail. So there are 4 possible outcomes for this experiment, right? Tossing two coins, we can get 2 tails. One head, one tail. First head, second is tail. And the first is tail, the second is head. The last one is both are heads. 4 possible outcomes. And for random variable X, we have only 3 possible values because X is counting number of heads, right? for the first outcome, TT, 0 heads, so x equal to 0. For those middle two possible outcomes, they're gonna produce the same value for x. So they both have x equals to 1 because they have one head in these two coins. Is that okay? So the first outcome corresponding x value is 2. So in this way, we link the outcome with the value for random variable x. Here, just pay attention. Notation-wise, we're using capital X to represent the random variable, and the lowercase x to represent the observed value for this random variable. So after we link the outcome with the value for random variable, what is a probability distribution function? A probability distribution function is a mathematical relationship or rule we assign to any possible value x of a discrete random variable x the probability of capital X equals to a specific value, small x. So next we're gonna introduce, there's a rule to assign each possible value for random variable of x its probability. In the last lecture, when we looking at those elementary outcomes from the sample space, we already figured out for those kind of experiment, tossing two coins, for each outcome, its probability is 1/4, right? Because there are 4 equally likely happened outcomes. For each one, the probability of it is 1/4. And we just learned the relationship between the possible value of x with those outcomes. We can assign the probability for the random variable x. Such like, what's the probability of this random variable x equals to 0? This is 1/4. The probability of capital X equals to 1 is 1/2 because it consists of 2 elementary outcomes. 2 elementary outcomes, the probability is 1/2. So this way, for each possible value of x, we assign a probability to it using the probability density distribution. Here we can represent this probability distribution using a probability histogram. In this histogram, for each bar, we have base 1. The height is represented by the probability for this associated value. So from this picture, you can see the probability distribution for random variable of x. And also you can see the summation of all of those 3 bars, the area of those 3 bars should be equals to 1 because the summation, the probability for the total outcome should be sum up to 1. So this is the probability distribution for random variable of x for this experiment. Next, let's look at another example. This time, we toss 2 dice. And we let the random variable be the sum of dots on the 2 dice. So we're gonna find out what's the probability distribution for random variable y. So what's the possible values for y for this experiment? We are tossing 2 dice. We're gonna observe the values for those 2 dice. Y is the sum of the dots on those 2 dice. The smallest possible value for y is what? It's 2, 1, 1. The largest possible value for y is what? It's 12, 6 plus 6. So there are such possible values for y, from 2 up to 12. For each one, we can looking at which elementary outcome for this value consists of, then we can figure out the probability for this variable, for random variable y equals to each specific value, right? For example, for y equals to 2, it consists of only 1 elementary outcome. For each elementary outcome, its probability is 1 out of 36. So for probability y equals to 2 is 1 out of 36. Yes?
So in this case,
No.
No.
Because it's impossible. We are tossing 2 dice.
But
The smallest one is 1, 1.
But it still has a probability of getting that unusual outcome, which is 0.
Yeah, there are certain events has the probability 0, but this one is completely impossible for this experiment, right? We just eliminate from the range of variable y. It's impossible.
Okay.
Okay. So otherwise, there are so many impossible values. You cannot list them all. We're only focusing on the possible value. So this is, in this way, we figure out the probability distribution for random variable of y. Is there any question here?
So in this distribution, you'll never have elementary outcome which has a probability equals 0.
No.
Is that correct?
No. Yeah. Is that okay? So here is just a probability histogram for this random variable y. And in practice, we should be familiar with relative frequency. So the probability can be actually estimated by the relative frequency. So if we repeat one trial a large number of times, then we can count how many times the interested event occurs. And then we're using this number divided by the total number of trials you have done. Then this way, we calculate the relative frequency for specific event. This can be used to estimate the probability. And the probability should be a number between 0 and 1. And this relative frequency histogram, if we just draw a graph about those relative frequency, then we can see it looks very similar to the probability histogram, given the condition that we repeat this experiment in a very, very large number of times. This is gonna be the relative frequency gonna approaching the true probability histogram. And here another concept we need to know through the biostatistics course is what's the difference between sample properties and population properties. In practice, we always analyze a data set. Actually, this data set is just a sample from the general population. And given a data set, we can calculate the sample mean and the sample variance in this way. And this is just tells you the basic properties for this data set. And in the other hand, for any samples, we actually have an underlying true population model. We make such an assumption about the true population model. And this is just be defined by probability distribution. Just given a probability distribution, we can also calculate the population mean and population variance based on the given probability distribution. So this is the difference between sample and the population. We're gonna talk about the difference between those two more in the following lectures. Here, just to remind you, you should be clear about the difference between sample and the population. So we just defined the random variable, and for random variable, we have a probability distribution. Then based on this probability distribution, we can figure out what's the mean and the variance for this random variable. Mean or expected value of x is denoted by ex, or a Greek letter mu. It's defined like this way. It's the summation of all the possible values, with each value is weighted by its probability. This formula is the summation of all the possible values for this random variable x. And also, for each value, it must be weighted by its probability. The expectation or mean of a random variable usually tells us what's the average value or what's the typical value for this random variable. So here, back to that tossing 2 coins example. Here I show you how to calculate the expected value for x. Back to this table, we already know the possible value for x and its associated probability. For each one of them, we can calculate the value multiply its probability. x multiply probability x equal to small x. So for each possible value, we calculate them, then sum up through all the possible outcomes. We get the expected value for random variable x. It is 1. So 1 is the average, or is the typical value for the number of heads when you are tossing 2 coins. Is that okay? This is show you how to calculate the expected value of x. Then what's the variance of a random variable? The variance of x is the expected squared distance from the population mean. So this calculation depends on the population mean. You need to first calculate the mean. Then for each possible value of x, you calculate the square of the distance from the mean. Then you got the variance. Do the summation through all the possible values. You got the variance of x. Take the square root of it, you get the standard deviation. So back to this example, we can calculate this quantity for each possible value of x. Sum all of them, you get the variance of x is 0.5. Here, I want to emphasize that both the mean and the variance we just calculated are based on the probability distribution. They are the population properties. They are not calculated from the sample data. Is that okay? Just based on the underlying probability model. This is what we call the population properties. So we have already talked about 2 types of random variables. One is a discrete random variable. So far, all the examples are about a discrete random variable. Next, we're gonna look at in details about the continuous random variable. Again, a continuous variable is possible values cannot be enumerated, and there are infinite number of possibilities for its values, and all the outcomes have probability 0 for every x. Here I just want to using an example to illustrate the properties for a continuous random variable. Look at this picture. This is a balanced spinning pointer. It can stop anywhere, right? So we let x, this is a random variable, to be the proportion of the total circumference it lands on. Is that okay? So what's the possible value for x? Then x could be any number between 0 and 1. But there are infinite possible values for x. Right? Just giving you any 2 very close number, you can always find a number in between them. So there are infinite possibilities for x. This x is continuous. They are not discrete or isolated. So you cannot enumerate all the possibilities for x. The value of x are infinite possibility. So x is continuous random variable. Is that okay? So for a continuous random variable, if we want to find the probability of x, its value between 0.25 and 0.75. What's the probability of x? From 0.25 to 0.75, the possibility for x is just half, right? If the x could be anywhere on this circle, so what's the probability x land on between 0.25 to 0.75? The probability is 1/2. However, because there are infinite possible values for x, each one is equal likely to happen. So when we talk about what's the probability for this continuous variable equals to a specific value, such like 0.5, it is 0, because there are infinite possibilities. Each one are equally likely to happen. So for each specific point, the probability is 0. This is the basic property for continuous variable. We can talk about the probability for this continuous variable within an interval. given a range, you can calculate the probability. But if you are talking about the probability for a continuous random variable equal to a specific value, it is 0. Is that okay? This is different from the discrete random variable. Still, let's continue working on the probability density function for x. For a continuous random variable, we usually give a density function. We call it PDF. It's just given like the format y equals to function of x. It's the probability density function for random variable of x. If we want to calculate the probability for this random variable of x between a and b, for the continuous random variable, this probability is just equals to the area under the curve between value a and b. The probability for random variable of x is between a and b is just calculate the area under the curve over this range, over this interval. So how to calculate the area under the curve? We need to use some calculus tools. We need to take the integration of this probability density function over this interval. So this is the probability for a continuous random variable. And the total area under the density function curve over the entire range of possible values for this random variable is 1. And we denoted it as we take the integration over this probability density function from negative infinity to infinity. This is including all the possibility, including all the area from this end to the other end. This area should equals to 1. Is that okay? This is for the continuous random variable. How to define its probability. At each specific value, the probability is 0. Then if we're looking at an interval, we need to take the integration, look at the area under the curve. There are some other properties for the probability density function of a continuous random variable x. The PDF has large values in regions of high probability. So if on the curve its value is high, then of course the area under it should be large. The probability for those values should be large. Is that okay? So it's obvious. If on the function it has large value, then its associated probability should be large. And also because at each specific value x, its probability is 0. So generally, all the following, there's no difference between probability for x less than a number or less or equal than a number. Because at that equal sign, at specific value, there's no probability, it's 0. So now, how to calculate the mean and the variance for a continuous random variable. So the expectation of a continuous random variable is defined like that way. You take the integration over all the possible values from negative infinity to positive infinity, and using this random variable x, multiply its probability density function. And the variance is calculated in this way. The function is x minus mu squared, then multiply its probability density function. Then you take the integration over all the possible values. Take the standard deviation, then you can get the sigma, the standard deviation. You take the square root on the variance. So far, we have talked about 2 types of random variable. Next, I'm gonna talk about 2 important distributions. The first one is the binomial distribution. This is for a discrete random variable. Before looking at the binomial distribution, here is the definition for Bernoulli trail. What kind of trail can be called Bernoulli trail? For Bernoulli trail, usually it has 2 outcomes, such like a heads or tails coin toss, a win or lose football game, or pass or fail automotive smog inspection. Those are all Bernoulli trials. For each trial, there are two possible outcomes, success or failure. And also the underlying success probability P is the same through all the trials. There are two outcomes, and also there's a success probability. And if we repeat those trials, each trial should be independent from the others. Those are Bernoulli trials. And the binomial random variable is defined based on the Bernoulli trial. If X is the number of success in n repeated Bernoulli trial with probability P of success, X is a Bernoulli random variable. So for the binomial, this X is a binomial random variable. For the binomial random variable, the success probability is the same in each trial, and all of those trials are independent. Then since this binomial random variable is based on those Bernoulli trials, we can figure out what's the probability distribution for a binomial random variable. It's just given like this one. This is the formula. This is the probability density for a binomial distribution, which is calculating how K success in n trial with success probability P. So you need to know the total number of trials n and the success probability P. Then you want to calculate what's the probability this binomial random variable equals to K. You just calculate it in this way. In this formula, there are two parts you can see. The first part, we call it, what's the number if we choose K from N. Choose K from N. This notation can be calculated in this fraction. The numerator is N factorial. The denominator is K factorial multiply N minus K factorial. And the factorial is defined in this way, such like if 100 factorial is just 100 multiplied 99 up to 1. So in this way, you can calculate the first part of the formula. This is actually counts all possible ways of getting K success and N minus K failures from N independent trials. So there are in total, if you do N trials, there are K choose from N so many ways to get K success and N minus K failures. And the second part is P up to the power of K multiply 1 minus P up to the power N minus K. This is just to calculate the probability for getting K success and N minus K failures. So there are such many ways, then you just multiply this number of ways to this probability. This is the total probability for getting K success in N trial with success probability P. Is that okay? So this is the probability density for binomial random variable. And for binomial random variable, if we know the number of total trial and the success probability, we know its mean just given by N multiplied P. This tells you the average number for a binomial random variable. This is the mean, the formula. Of course, we can derive those formula based on those probability calculations. Here, you can just take it as a fact. This is the mean. This is the variance for a binomial distribution, binomial random variable. The mean is N multiplied P, and the variance is N multiplied P, the probability of success, and then multiply the probability of failure. Is that okay? For the binomial distribution. Now let's look at one exercise. How to use those probability properties for binomial random variable to do some simple calculations. In this example, newborns were screened for HIV in a Massachusetts hospital. the positive rate for inner city baby is P equals to 0.01, is 1%. That is the success probability is 1%. If 500 newborns are screened, so N equals to 500. The question is, what's the exact binomial probability of 5 HIV positive test results? How to do this? So the number of HIV positive test result is a random variable, right? If we let X to be the number of HIV positive test result among those 500 newborns, this is a random variable. And from the problem, we know is this random variable follow a binomial distribution, right? Because for each newborn, you're gonna get a test. And for this test, we know the positive rate is 1%. We do it 500 times. What's the exact probability for X equals to 5? So this problem just asks you what's the probability of X equals to 5, and X is a binomial distribution with the total number of trials is N, success probability is P. So we're gonna calculate P, the probability X equals to 5 using the probability density function for a binomial random variable. And then how to figure out this number? Actually, there are all those basic functions in different software. I don't care which software you're gonna use to figure out the number. Here, I just show you how to figure out this number using the Excel. I assume everyone know how to use the Excel. Is that okay? So in Excel, how to calculate this complicated formula? We can use this function binom dist. And there are 4 elements in this function. The first element, you give the number of success. Here is X equals to 5. So the first element should be 5. Second element is number of total trial. The third element is the success probability. And the first element, it is either false or true, just indicate whether it is a cumulative distribution you are calculating. Here, you are calculating exactly X equals to 5, so the first element should be false. It's not a cumulative probability, just for one specific value. Is that okay?
So what would a cumulative?
Yeah, cumulative is the probability X equal or less than 5. So from this far left end up to this point is a cumulative probability. If you are looking just one number for the discrete random variable, this is you put a false in the first element. It's okay? This is question 1. What's the second question? What's the exact binomial probability of at least 5 HIV positive test results? We're still using X be the number of HIV positive test results. Here, we are asking at least 5. That was the probability of X greater or equal than 5, right? We need to calculate this probability. For this probability, you see this number could be from 5 up to 500. It's impossible you're gonna enumerate the probability in this way. So a simple way is that we can calculate the probability for X less or equal than 4 than using 1 minus it, because we can easily calculate the complementary event, the probability for the complementary event. Then we just first calculate the probability for X less or equal than 4. Is that okay? So we want to calculate X greater or equal than 5. It's equivalent to 1 minus probability X less or equal than 4. And this probability is a cumulative probability. We can use the same binomial dist function in Excel to get this number. Here you need to put the first elements to be true because we are calculating the probability from 0, 1, 2, 3, 4. Is that okay? Any questions for the binomial random variable? Okay, then we move on to the second distribution. This is another important distribution. It is normal distribution. Normal distribution is also called Gaussian distribution. It's named after the mathematician Carl Gauss. And another name for this distribution curve is bell curve because the shape of this curve looks like a bell. Is that okay? So normal distribution. Normal distribution is very useful because lots of things closely follow a normal distribution, such like the heads of people, errors in measurement, blood pressure, scores on a test. And besides, many other distributions can be approximated by normal distribution. So it's very useful, yes.
I actually have a question about Bernoulli distribution. If we go back to one of the example about exact and fine success. So if you simply think the P, which is success probability, which is 0.01, and if you think that there are 100 patients testing for HIV, you have one success rate. I mean,
Expected,
yeah.
expected value is 1.
So if you have 500 patients, then you're gonna have 0.5 probability.
You are talking about the expected value. If you're using the n multiply p, that is expected value. So you're talking about 100 people, you are expecting to have 1 positive result. If we are doing 500 newborns, we are expecting to have 5 positive results. But here, we just looking at the exact probability. What's the possible? What's the probability? It's a very slight probability to observe 5 positive results.
Then what is the difference between expected probability and this Bernoulli probability?
Expectation is expectation, and probability, you just calculate the exact probability. The expectation is the on average. On average, what's the average value for this random variable?
So this is not
The most common value. It's still possible, right? The most common value for these 500 newborns more likely is around 5 because the success probability is 1%. Most likely is 5, but there's still possibility we can observe 10 newborns has positive results, right? In reality, although the underlying successful probability is 1%, some small possible event could still happen, happen, right? Although the chance is very small, it still could be happen. So what's the possibility we're gonna observe 5 positive results from this experiment? It's about 17%. It's not very high, but still could happen. Any other questions? So then we can move on to normal distribution. So here, just to show you, normal distribution is a very, very common distribution. And a lot of statistical method is based on the normal distribution. So it's really important to learn what is normal distribution. So here, just give you the probability density function for normal distribution. You can see in this function, actually there are only 2 parameters, mu and sigma. Mu is just the mean of this normal random variable, and the sigma square is just its variance. So a probability distribution density for a normal distribution is determined by its mean and variance. So here is more properties for normal distribution. A normal distribution, it is symmetric, and also its mean, median, and the mode are at the same number. from this picture, you can see about there are 50% of values less than its mean because it's symmetric. For normal distribution, its location is measured by its mean, by the mu. Looking at the picture, there are two normal distributions. They have the same variance but a different mean. For this dashed normal distribution, its mean mu2 is larger than the other one. So this normal distribution, its mean is larger than the other normal distribution. So the location is determined by its mean. For those two normal distributions, they have the same mean. The center are at the same point, but they have a different variance. Variance tells you how spread is this distribution. This dashed normal distribution, its variance is larger. So for this distribution is more spread out than the other one. The other one has smaller variance, so it's more concentrated around its center. The other one, if you have the larger variance, it's gonna be more spread out. So the variance just tells you the spread of this normal distribution. And here, we're gonna focusing on a special normal distribution with a mean equal to 0, variance equals to 1. We call it the standard normal distribution. If we put mean 0, variance 1, we get a standard normal distribution. And we will see that any information concerning a general normal distribution, it can be obtained from the appropriate manipulations of an standard normal distribution. Actually, for any given general normal distribution with general mean mu and a variance sigma square, we can transform it to a standard normal distribution. So next, we're just focusing on the property of standard normal distribution, because whenever we give a general one, we can always transform it to standard distribution, standard normal distribution. So here's the density for standard normal distribution. Normal 0, 1. And when mu equal to 0, sigma equals to 1, its density function is simplified like this one. And for standard normal distribution, looking at this graph, you can see there are about 68% of the area under the standard normal density lies between -1 to +1. For the general normal distribution, we're gonna say that there are 68% of the area under the general normal density lies between negative sigma to positive sigma. And there are 95% of the data actually between the line from -2 to +2 for standard normal distribution. There are 99% of the data lies between from -2.1 to +2.1. This is always true for the standard normal distribution. You can see most of the data is within the plus and the -3 standard deviation for normal random variable. Then, what's the cumulative probability? The cumulative distribution function for a standard normal distribution is defined by capital FA. And by the way, we always use capital letter Z to denote a standard normal distribution. When we use the capital letter Z, we just indicate Z followed to a standard normal distribution. And in Excel, how to calculate the cumulative probability for a standard normal distribution, you can use this function, the norm as this. Here, just show you how to calculate the probability of standard normal random variable between an interval from A to B. This probability just can be calculated by the cumulative probability at B minus the cumulative probability for standard normal random variable at A. Such like here we calculate the probability for standard normal random variable between -1 to 1. It's just f1 minus f -1. And for f1 and f -1, you can use this Excel function to get it. Is that okay? So for the first figure, this is just to show you the probability for z less than 1. And the second figure is the probability for z less than -1. And using the error in the first figure minus the error in the second figure, the difference of it is the probability or the error between -1 to +1. Here is how to calculate a standard normal variable. Was the probability greater than A, greater or equal than A? You just calculate what's the probability less than A, then using 1 minus it, you can get it. Then how to standardize the normal distribution? Given you a general normal distribution, we can always do some transformation to make it be a standard normal distribution. For the left graph, it represents a general normal distribution with mean mu equals to mu and the variance or standard deviation equals to sigma. We want to transform it to a standardized normal distribution with mean equal to 0 and sigma equals to 1. We just, for the original random variable x, we use x minus its mean divided by its standard deviation. This has become a new random variable. We call it z. Then z just follow to a standard normal distribution.
What's x?
X is the original general normal distribution with mean equals to mu and the standard deviation is sigma. For the left figure is x. For the left figure is x. X is a random variable with mean equals to mu and the standard deviation is sigma. If we minus mu from x divided by sigma, here become a new random variable. This is represented by z. Then z is follow a standard normal distribution because its mean is mu, mean gonna be 0 and the standard deviation is 1. Is that okay? So if x is a general normal distribution with mean mu variance sigma square, we have this, after this transformation, we know z is a standard normal distribution. So if we are asked to calculate what's the probability for x, which is the general normal distribution, what's the probability x is between A and B, we can first transform it to a standard normal distribution. We minus mu divided by sigma on those 3 items together. You can see the middle part become to z, and then for z, a standard normal distribution, we can figure out its cumulative probability. Then we can calculate the probability for x on this interval. So here just one example. If x follow a normal distribution with mean 80 and the variance is 12 squared, what's the probability for x is on the interval from 90 to 100? So we can do the transformation. We minus its mean on all of those 3 items and divided by its standard deviation. The middle part is x minus 80 divided by 12 becomes to a new random variable z. Z, we know it is follow to a standard normal distribution. And then we can calculate the cumulative distribution for standard normal distribution. Either in the old age, we need to check the table to find this number, And right now, we can using some function from different software to figure out this number. So in this way, we get the probability for x between 90 to 100. Is that okay? So when we talk about the probability for a normal random variable, my suggestion is always draw a sketch of normal density, and then you can figure out which area, on which interval you are calculating. Here is another exercise for normal density distribution. Suppose we know that among men aged 30 to 35 who have ever smoked, the mean number of years they smoked is 12.8 years with a standard deviation of 5.1 years. Assuming the duration of smoking is normally distributed, what's the proportion of men in this age group have smoked for more than 20 years? So in this problem, we first define the random variable. The random variable x is number of years for a man aged between 30 to 34. How many years, if it's ever smoked, how many years it smoked. We are calculating what's the probability x greater or equal than 20, right? And also from the problem, we know x is normally distributed. What's the mean for x? 12.8 years. Its standard deviation is 5.1. So we know the mean and the variance for x. We are calculating what's the probability x greater than 20. So for the probability x greater than 20, it's the same way we calculate first what's the probability x less or equal than 20. For x less or equal than 20, there are two ways to figure out the number. One way, you can use the norm dist function in Excel directly. Just gives the cutoff point 20 and the mean and the standard deviation for this general normal variable, and also tells it you are calculating the cumulative probability. Then this function just gives you the number for probability x less or equal than 20. Or you can first transform this x into a standard normal distribution. You minus this mean divided by standard deviation. You transform it to a standard normal distribution. This number equals to 1.412. Then you can use this simple function, the norm standard distribution function. Just plug in this number. It also gives you the cumulative probability for a standard normal distribution at the point 1.412. This is just show you how to using Excel functions to calculate these normal probabilities. Any questions? Yeah, I think this is pretty much for today's lecture. If you have any question, you can ask. We talk about two probability density distribution. One is a binomial distribution. This is for the discrete random variable. The other is this one, the normal distribution, is for a continuous random variable. And the homework from last week and also this week gonna do this Sunday together. All of those, the homework for the 3 lectures gonna be due together on this Sunday. Okay?